In this video, we will take the theory that we discussed in the previous video and implement it in code using Qiskit. I will go through the Python code step by step, and we will build what we introduced before. A variational quantum classifier that learns to classify input data according to the XOR pattern. First, we need to import a few libraries. We start by importing Qiskit itself. This is the general Qiskit library that brings in a wide range of useful tools. Then we import quantum circuit from Qiskit. With this we can build our quantum circuits. Next, from Qiskit quantum info, we import state vector and sparse Pauli op. State vector applies all the gates that we define, such as the RY rotation and the C0 gate, and then interprets the result mathematically. It calculates the final quantum state in the form of a state vector. Sparse Pauli op is what we use to define our observable, in this case the Pauli C operator, which we will measure later on. Data class is only there for clarity. Later we will define a small data class where we collect information for training, such as the number of steps or the step size. This is not strictly necessary, but it makes the code much cleaner and easier to read. Finally, NumPy is the standard mathematical library. We will need it, for example, when we work with functions such as the exponential. Next, we define our inputs in the variable x. We create one array that contains 4 smaller arrays, 0, 0, 0, 1, 1, 0, and 1, 1. We do this with the NP array. Why? Because with the array function from NumPy we can perform mathematical operations much more easily. For example, we can call pointMean to calculate the average of all entries in the array very quickly. This makes the later steps much simpler. And this is why we use NP array here. Next, we define our labels in the variable y. In the same way as we did for x. These are the outputs that should come out in the end. For the pairs 0, 0 and 1, 1, the label is -1, and for the pairs 0, 1 and 1, 0, the label is +1. In the XOR problem, -1 stands for the output 0 and +1 stands for the output 1. In the next step, we define our function for the feature map. We call this function feature map circuit and we pass it the variable x. This will simply be the input data that we defined earlier. Inside the function, we create a quantum circuit with 2 qubits and store it in the variable qc. Then we loop over each input. We do this with a for loop over the 2 qubits. For each qubit we check if the input is equal to 1, we apply an x gate to it. If the input is not 1, then we do nothing. Why do we do this? When we create a quantum circuit, the qubits are always initialized in state 0. If the input bit is 1, we rotate the qubit by 180 degrees, which flips it from the 0 state into 1 state. So if the input is 1, we set the qubit into the state 1. In the next step, we define our function for the variational ansatz. We pass this function the variable fader, and later on fader will be defined as a vector or an array that contains all the parameters we want to train. Inside the function we again create a quantum circuit with 2 qubits. We have to do this here because we are inside a function. We could also have defined the circuit globally at the start and reused it, but in this case I chose to define it locally. On this circuit we apply an RY gate with QC.RY. First we apply it to qubit 0 and we rotate by the value of fader 0. As I mentioned, fader is our array of parameters, so here we take the first entry and use it to rotate qubit 0 around the y-axis. We then do the same for qubit 1, this time using the second parameter, fader 1. Next we add a C0 gate with QC.CX. We define qubit 0 as the control and qubit 1 as the target. Finally, we apply another RY gate on qubit 0, this time with the third parameter, feeder 2. And that completes our variational ansatz circuit. In the next step, we define a function that combines our feature map and our variational ansatz. We start by creating a new quantum circuit, and then we use compose to extend this circuit with the feature map. Since our feature map function already returns a circuit, we can directly add it here. The argument in place equals true simply means that we do not create a copy, but instead extend the existing circuit. We then do the same with the variational ansatz and finally return the circuit. So what this function does is to put together the two building blocks, the feature map and the variational ansatz. We could also have written everything in one single function, but I decided to separate it like this. Of course, both ways would work. Next, we define our observable in the variable CQ0. We use the function sparse Pauli op from sparse list. Here we want to define a Pauli operator, and specifically we define the Pauli C operator applied to qubit 0. The value 1.0 stands for the weighting. By default, the Pauli C operator returns either +1 or -1. That is exactly what we want here. If, for example, we set the weighting factor to 5.0, the operator would no longer return plus or -1, but plus or -5. So this coefficient directly scales the measurement outcome. Now we define the expectation value, which means we need a function that returns it. For this, we create the function predict expectation, where we again pass in our input and the parameters. Inside, we call function build model circuit so that we get the full circuit we just built. Then we calculate the state vector. As I explained in the last video, the state vector takes all the operations from our circuit, applies them mathematically, and gives us the final quantum state in the form of a vector. We store this in the variable psi. In the next step, we calculate the expectation value with this line. What this does is compute the expectation value of the state vector psi using as the basis the observable CQ0 that we defined earlier with the Pauli C operator. We then take only the real part to make sure the result is a real number and has no imaginary component. Now we will define the function predict label. The purpose here is to produce the correct outputs as 0 or 1 and not -1 or +1. First we call the function that computes the expectation value, and then we return 1 if this expectation value is greater than 0, and if it is less than 0, so it goes towards -1, we return 0. We will need this later in the evaluation when we actually print out the results, because at that point we want to present them as zeros and ones. The next function defines the loss that we calculate. Here we pass in the inputs x, then our labels y, and again feeder our parameter vector. We then store an array in the variable preds. This array contains nothing else but each individual expectation value for every input. In other words, we go through each input, calculate its expectation value and store it in this array. After that, we calculate the loss as follows. We take the difference between the expectation value and the corresponding label y, which is either +1 or -1. This difference is the error. We then square the error so that all values are positive and larger errors are penalized more strongly. With NP mean, we calculate the average of these squared errors across all inputs. This gives us a single number that represents the average error over the entire dataset. We do this because instead of having 4 separate error values, one for each input, we want a single number that summarizes the performance of the model. And that is what this function returns. Now we are ready to define the function for calculating the gradient. We pass this function our inputs, our labels, the parameter vector and EPS, and I will explain in a moment what EPS means. We then define the variable grad, which is our gradient. At first we set it to the 0 vector. The important part here is that this vector has the same size as our parameter vector feeder, because the gradient must of course have one entry for each parameter. Next, we loop over each parameter. The method we use here is called the central difference quotient, which is a standard technique in numerical differentiation. It is actually quite simple to understand. For each parameter, we create two slightly modified versions of our parameter vector, t plus and t minus. To do this, we first copy feeder so that we do not overwrite the original. In t plus, we increase the current parameter by a very small step, EPS. In t minus, we decrease it by the same small step. All the other entries of the vector remain unchanged. We then call our loss function twice, once with t plus and once with t minus. The result is two values, which we call f plus and f minus. F plus is the error when we slightly increase the parameter, and f minus is the error when we slightly decrease it. Finally, we calculate f plus minus f minus divided by 2 times EPS. This is the central difference formula, and it gives us the derivative of the loss with respect to the current parameter. We repeat this process for all parameters. At the end, the function returns the full gradient vector, which contains the derivative of the loss with respect to each entry in feeder. Now we define our class, which I call trainConfig. What we do here is set up the main training parameters. First, we define the step size, or learning rate. Then we specify how many training steps we want to perform. Next, we set EPS, which we just used for the numerical gradient calculation. And finally, we have verbose, which is set to true. This simply means that the training will print out the intermediate results step by step, instead of everything running silently in the background. Now we come to the actual training. For this, we also define a separate function, which we will call trainVQC. We pass it the inputs x, the labels y, the initial parameter vector feeder, and CFG, which is simply an instance for our trainConfig class. Inside the function, we start by copying feeder 0 into feeder. The reason we do this is that we want to work on a copy of the parameters rather than overriding the original values. We also create an empty array called history, which we will use to document the loss during training, so we can later see how it evolves. Next, we set up a for loop for t in range CFG steps. This means we will repeat the training process as many times as the number of steps we defined in our configuration. So first t equals 0, then t equals 1, and so on, until we reach the final step. At each step, we calculate the loss by calling our loss function. We then append this value to the history array and so that the full training progress is recorded. After that, we have an if condition with two parts. The first part checks whether CFG verbose is set to true or false. This decides if we want to print intermediate results or not. In our case, it is set to true, so this condition is fulfilled. The second part of the condition checks whether the current step number is divisible by 10 without a remainder. What this does is make sure that we do not print every single step, but only every 10th step. So steps 0, 10, 20, 30, and so on. Each time the if condition is satisfied, we print the current step number, the current loss, and the parameter vector feeder with all three parameters. Next, we calculate the gradient by calling our numerical grade function. Then we update our parameters based on the gradient. How do we do this? I already explained it in the previous videos, but let me repeat it briefly here. First, we multiply the gradient by the learning rate. The reason for this is that the gradient itself could lead to steps that are too large, and the learning rate lets us control the step size. So we scale the gradient with the learning rate. Then we see the expression feeder minus equals, and this is simply short Python notation for saying take the current feeder and subtract the learning rate times the gradient and store the result back in feeder. Why do we subtract? The gradient always points in the direction where the error increases most strongly. If the gradient is positive, that means we are on an upward slope. And increasing the parameter would make the error larger. Since we want to reduce the error, we go in the opposite direction and therefore subtract. If the gradient is negative, that represents a downward slope. In this case, decreasing the parameter would also increase the error, so we want to move in the opposite direction and increase the parameter. Mathematically, this works out because the minus sign from the formula and the negative sign from the gradient cancel out and we add to the parameter. At the end, the function returns both the optimized parameters and the full training history, which contains the loss values from all training steps. Next comes this line. With this line we initialize our first parameter vector feeder. Here we simply choose random values between minus 0.5 and plus 0.5. The size is 3 because we only want it to contain the 3 parameters of our variational circuit. With these two lines, we now define CFG as equal to train config. This is the class we described earlier when we introduced the training function. Here we create an instance of it and store it in CFG. Then we call the training with this configuration and save the results in the variables feature star and history. In these two lines, we store the results in pred.exp and pred.label. In pred.exp, we create a numpy array by calling the predict expansion function with our new feeder star. This parameter vector already contains the optimized values, since we have completed the training with train VQC. What we get here are the expansion values for each of our inputs, calculated with the optimized parameters. In pred.label, we then store another array, this time with the predicted labels. Here we map -1 to 0 and +1 to 1 so that we can get the classical XOR pattern. Now we are almost at the end. We add one more print statement. Here I use a for loop with I and x in enumerate x. What enumerate does is go through every entry in x and give us two things. First I, which is the index, so 0, 1, 2 and so on, and second x, which is the actual entry itself. In our case, the inputs 0, 0, 0, 1 and so on. Inside the print function, we then display the input, the expansion value, the predicted label, so what the model actually outputs, either 0 or 1, and finally the true label, which is what should have come out according to the XOR pattern. In the final step, we simply remap our labels with Y classical. Then we calculate the accuracy with NP-mean by comparing the predicted labels with Y classical. If they all match, we get 4 times true. Since true is interpreted as 1 by numpy, it means 4 times 1 divided by 4, which gives us 1 or 100% accuracy. We print this value to show the accuracy of our model. Finally, we also print the final loss. And that's it. And now we can run our code. At step 0, we still see a relatively high loss, and we get our 3 randomly generated parameters. By step 10, the loss has already dropped to something very close to 0, and we see the updated parameters. So already from step 10 onwards, the model performs very well. This means that in practice it would probably be enough to run only 20 steps or maybe even just 15. Here I let the training run for 100 steps, but we can see that the outputs for all inputs are already correct, and I tested this multiple times. The results are always consistent, so we can conclude that our code works correctly. Now let me add a few final remarks about the code itself. We did not actually simulate this on a quantum simulator or run it on a real quantum computer. That would also be possible, of course, but what we did here was simply calculate the state vector directly. This shows that the idea works in theory. But if we wanted to test it realistically, either on a simulator with noise or even on real quantum hardware, we would need to rewrite parts of the code so that it runs on the actual backend. I did not do that here because the main goal was to demonstrate the theoretical possibility and to show the transition from a classical problem into the quantum world. For those of you who watched the other videos in the series, you will remember that in the classical case we needed about 5000 training steps. The reason this quantum version converges much faster is simply that we only use 3 parameters here. The classical model had more parameters, so it took longer for the network to adjust them correctly. If we had dimensioned both models the same way, for example a classical model with only 3 parameters, or a quantum model with the same number of parameters as the classical one, the number of steps required would be roughly the same. So what I want to make clear is this. For this specific problem, there is no quantum advantage. The quantum model is not inherently faster. The last point I want to mention is that I plan to make another video where we scale this up to more inputs. In this example we only had 2 inputs, but the idea is to extend it so that we can work with more, say 10 input bits. With small inputs we can still simulate everything easily on a normal computer. But once we go to larger input sizes, something like 10 inputs, classical simulation becomes infeasible, and at this point we would need a quantum computer. In that future video I want to show how the scaling works, and we could then also run it on a real hardware to see if it works in practice. Of course we would not train the entire model on a quantum computer, but it would still give us a realistic demonstration. So that is the plan for the next video. I hope everything up to this point was clear and that it was helpful for you. As always, feedback and comments are very welcome, and with that I'll see you in the next video.